Okay, this lesson is going to be on rates of change and limits. This is the first of 3 lessons that we will cover in section 1.1. Okay, so we're going to talk today a little bit, we're going to start talking about limits. Okay, now there's a definition here that you can read, but the probably the most important word in this entire definition is right here, approaches. Okay, so when we're talking about a limit, it's not what the function equals, it's what the function is approaching. So down here, you can see that there's space for 3 graphs. So we're going to draw some graphs, and we're going to talk about the limit, and we're going to talk about the function, because those are different. Okay, so on the first graph, I'm just going to draw some random function. Okay, I'm going to call this f of x. It's a function. Okay, and I'm going to pick some random spot on the x-axis. I'm going to call that c, which then means if this dot, which is on the function, evaluated at c, this ordered pair would be c, comma, f of c. All right, hopefully that makes sense. I'm just going to call this particular spot over here on the y-axis, I'm going to call that L. It's some number. I don't know what it is because this is very, very generalized. Okay, but let's talk about this in terms of limits versus the function. Okay, so the limit here, and we get to use this really cool notation. The limit as x approaches c of that function equals that number L. Okay, what that means is, and let me switch colors so I can really kind of point this out. As I am going closer and closer and closer to C, I'm approaching, that's approaching on the x-axis. My y value is approaching L. Okay, now, in this particular situation, the function itself, f of c, also equals L. Okay, now that's not always the case. Okay, I'm going to draw a different example. Okay, so let's look at the middle guy. Okay, so I'm going to draw this function. All right, so here at C, this is the ordered pair. When you put C into this function, that's what comes out up here, up at the top. All right, it doesn't exist here. That's an open hole. All right, so this is L. All right, so then when I try to plug in the bottom, and when I plug when I plug C into F, I get something that is not L. Okay, but the limit as I'm approaching C, right, as I'm headed towards C from the left, from the right, I'm still approaching L. Okay, so again, the function doesn't actually equal L, but the limit does. Okay, so what about this third example over here? What if I just had this point discontinuity? I'm calling this f of x. This is still c, this is still L. Here, f of c is not defined. Okay, when you try to plug c into that function, nothing happens. Okay, but the limit, again, it's what it's approaching. Okay, not what it actually equals. It's just what the heck is that getting really, really, really close to? The limit as x approaches c of f of x is still L. Okay, So now for these next two examples, we're gonna have to do them in the graphing calculator. Okay, so I've switched over to Desmos because you guys don't have your graphing calculators yet. Okay, so if you're still looking at the note page, you can see that it says sine of x over x, and we're trying to find the limit as x approaches 0. Before I even type that in, I want you to recognize that if I tried to actually plug in 0, that function doesn't exist. There's an x in the denominator, which means that I would really be plugging in 0 into the denominator, and that just doesn't work. So even though this graph shows up, right, and when I look here at this x value of 0, it looks very, very much like the function exists right here. It doesn't. Okay, but that's okay. We're not trying to evaluate the function, we're trying to evaluate the limit, right? So as I zoom in, you can still see, even though Desmos is not actually showing me that it doesn't exist there, the function is approaching 1. All right, so when I go back to my note page, I will fill in that value of 1. Let's see, and then if I'm looking at the notes correctly, there's another one. Let's see what x squared minus 9. Oh, never mind, I didn't get rid of that. Let's try this again. X squared minus 9 divided by x minus 3. Okay, so here's my picture, right? It looks like a line. It looks like when we are approaching 3, right? So 3 is right here on the x-axis, so right here, it looks very, very much like that should equal 6, right? But if you think about it, when I plug 3 in here into the denominator, actually the top and the bottom, it equals 0 over 0. This function doesn't actually exist at 3. Hopefully you also learned that in pre-cal last year. There is a hole in this line. There is a point discontinuity at 3. Desmos doesn't show it, but you can definitely see that the limit, as we are approaching 3, right, here's 3, is 6. Okay, I'm back. So based on the graph that we just did, this one equaled 1 and this one equaled 6. Okay, so now sometimes you only are looking at a right-handed limit or a left-handed limit. The notation there is pretty easy. Let me write those in for you. So this would be... All right, guys, that's the end of the first lesson. I hope that you wrote down every single thing that I said in my video and that I wrote on my notes, because I will be checking it tomorrow for accuracy, for neatness. I need to be able to actually read your stuff. So yeah, that's how this is going to work. You're going to watch those videos every night, take the notes. I will check them the next day. You'll get credit for them. And then we'll do actual calculus in class without any cell phones, without any Chromebooks, without any cheating devices, just your brains, because you got some good ones. All right, see you tomorrow.